In this video, we will learn about the ideal gas equation. Now, the ideal gas equation is PV equals nRT, where P is equal to the pressure in kilopascals, V is volume in liters, N is the number of moles, R is the gas constant, which is 8.31 joules per Kelvin per mole, and T is temperature in Kelvin. Okay. Now you should be familiar with pressure, volume, number of moles, just like Kelvin. So 0 degrees is equal to 273 Kelvin. So if you want to convert Celsius degrees to Kelvin, you just need to add 273 to it. Okay, so in some questions you may be given pressure in ATM, like maybe 1 ATM, 1 bar, and basically 1 ATM, so 1 atmosphere, is equal to 101.325 kilopascals. And 1 bar is equal to 100 kilopascals. Now you just need to memorize these, okay? So you can convert from ATM or from bar to kilopascals. Now, if you are given a question that asks you to find the, let's say, volume of a gas at STP, so STP, which is standard temperature and pressure, you can just use the volume formula in number of moles, so N equals volume of the gas over the molar volume, and the molar volume is always equal to 22.4 per mole. Now let's try an example. Let's say we had a question that says calculate the volume in liters occupied by 0.24 moles of nitrogen gas at STP. So since this gas is an STP, so standard temperature pressure, we can just use N equals V over molar mass or molar volume. So volume is equal to N times molar volume, 0.24 times 22.4, which is approximately equal to 5.376 liters. So another one, let's say calculate the volume in liters occupied by 3.5 moles of oxygen gas at STP. 3.5 moles of oxygen gas at STP. So volume is equal to the number of moles times molar volume, so 3.5 times 22.4. That's equal to 78.4 liters. But let's say we had a question that goes, calculate the volume in liters occupied by 2.24 moles of oxygen gas if the pressure is 200 kilopascals at 50 degrees. Now we need to use the ideal gas equation here. So PV is equal to nRT. And we're trying to calculate V. So rearrange the equation in terms of V. So V is equal to nRT over P. Now we have the number of moles. R is the gas constant, 8.31, and T is 50 degrees. But make sure you convert degrees Celsius to Kelvin first. So you add 273, so that becomes 323 Kelvin. So that's our temperature, and our pressure is 200, because it's 200 kilopascals. So substitute the values in. 2.24 times 8.31 times 323 over 200. And we get 30.06 liters of oxygen gas. Okay, and our last question will be question 2, and it says determine which sample of gas contains the greater amount of particles? Or it should say, particles in moles. 3.2 liters of nitrogen at 25 degrees at a pressure of 1.2 bar, or 2.5 of helium at 23 degrees, that's 23 degrees at a pressure of 1.2 atmosphere. So let's do 3.2 liters of nitrogen at 25 degrees at 1.2 bars. Now 1.2 bar is equivalent to 120 kilopascals, and 1.2 atm is equal to 1.2 times 101.325 kilopascals. 25 degrees is equal to 298 Kelvin, so we add 273 degrees, or well, just 273 degrees, and 23 degrees would be 296 Kelvin. Okay, so let's do the nitrogen first. So PV is equal to nRT. We're trying to calculate the number of moles. So number of moles is equal to PV over RT, and that's equal to 120 times volume, 3.2 liters, over 8.31 times 298. That's equal to 0.155 moles. For the hydrogen now, on a helium, we get skip that step. N equals PV on RT. PV, so pressure times volume, is equal to 1.2 times 101.325 times 2.5 over 8.31 times 296. And that's equal to 0.124 moles. Therefore, we can conclude that the nitrogen sample has a greater amount of particles in moles. So that will be the end of our ideal gas equation video, and we use this a lot in gas stoichiometry, which we will cover in another video.